Astronomy equations. Let's start with measuring the distance to a star using parallax angle. Parallax is the apparent shift in the position of a star or any other stellar object against a distant background when observed from two different locations on the Earth. For instance, if you hold a pebble and close your left eye looking at it from the other, then you do the same thing and switch to the right eye and close the left eye, the pebble will shift. It will shift its relative position. The angle of shifting between these two positions can be used in order to measure the distance using the tan. Why? Because the tangent is equal to the opposite, the tangent of the angle is equal to the opposite side of the triangle, that would be the displacement, divided by the distance from the observer to the object being observed. This is how we get it. So the relative position, the pebble shifts its relative position. The angle between these two positions from your vantage point is the parallax used in order to get the distance from the observer all the way to the object being observed. For the sake of the example, let's now use this coin instead of the pebble. At first, I will hold it in front of me. I will close the left eye, look at it from the right eye. Then I will switch by closing the right eye and looking from the left eye. You see it had moved. If you do the same thing, you will notice that the coin had displaced, had moved a certain distance. Now, as you plot the line from your right eye to the left-sided coin, observed from the right eye, and from your left eye to the left-sided coin, actually from the left it would be to the right, and from the right it would be to the left, just as you see here in this illustration, you would get the parallax angle, because we already know the distance between both of our eyes, correct? And when you measure the distance of displacement of the coin from left to right, you get the angle. From the angle, I can get, by measuring the tangent, by the way, because the tangent of the angle is equal to the opposite side, which would be the displacement of the coin, in this case, the displacement of the star being observed from two vantage points on two opposite sides of the Earth. We can get from that the distance to the star, because we have the angle, correct, and we have the distance from one side of observation to the other side, from one astronomic telescope to the other astronomic telescope. This is how we get the approximated distance to a star. Now here's the formulas that we're going to explain further in the second slide, or the next slide. 1 arcsecond is given by 1 divided by 3,600, just like 1 hour has 3,600 seconds. So 1 over 3,600 degrees is equal to 0.00028 degrees. A full circle is 360 degrees, 1 degree is 60 arc minutes, and 1 arc minute is 60 arc seconds. The distance in parsec, measured in parsec, 1 parsec is actually approximately 3.26 light years. 1 light year is the distance traveled by light over a period of an entire year. So the distance is equal to 1 divided by p, which is the parallax angle. The angle is measured in 1 arcseconds and the distance in parsecs. 1 parsec is when a star will shift in 1 arcsecond after the Earth moves 1 astronomical unit, which is the distance, by the way, from the Earth to the Sun. A full circle is 360 degrees. 1 degree is 60 arc minutes. This is how we get the arcsecond, and 1 arc minute is 60 arc seconds. So 1 arcsec is equal to 1 divided by 306 or 3,600 degrees, which is 0.00028 degrees. The distance in parsecs is equal to 1 divided by p, measured in parsecs. 1 parsec is approximately 3.26 light years. 1 light year is equal to the distance traveled by light in an entire year. Apparent versus absolute magnitude method. So lowercase m is the apparent magnitude or brightness, how bright the star look from our perspective, how does it appear from the Earth or an observer on the Earth. Capital M is the absolute brightness or absolute magnitude. Okay, how bright it would appear at a distance of 10 parsecs. So lowercase m minus capital M is equal to 5 log base 10 d, which is the distance, minus 5. This is the formula. So log base 10 d is equal to m minus m plus 5 divided by 5, which leads us to 10 to the power of these on both sides. 10 power log base 10 d is equal to 10 to the power of m minus capital M plus 5 divided by 5. So 10 log base 10 d would give us simply d, okay, equal to 10 to the power of m, lowercase m, which is the apparent magnitude, minus capital M, magnitude or brightness at a distance or from a distance of 10 parsecs, plus 5 divided by 5. This is how we get the distance to the sun or to the star being measured. To measure the apparent magnitude lowercase m, we use a photoreceptor like a CCD cam detector. On a telescope, we detect the amount of flux being received by the lens. The flux is the light energy, okay, that is being received from the star by the device. The flux is actually how much watt per meter square is being received from the signal. Then the brightness is converted to a logarithmic magnitude scale. As an example, Sirius is minus 1.46, okay, in order to avoid having colossal values that are no longer practical and easy to work with. Usually, you would have already calculated the distance and you use that to get the absolute magnitude, which is the brightness of light at 10 parsecs. So it can be both ways, but usually you calculate the distance to get the absolute magnitude, because the distance is retrieved from d equal to 1 over p, the formula that we've seen that is measuring the distance based on the parallax angle. Measuring the distance using luminosity. Let's first figure out how to get the temperature of a star. It will come in handy in a moment. In 1900, physicist Max Planck was able to find how to measure a body's temperature based on its wavelengths or color, so to speak. And he won a Nobel Prize for it, by the way. So the temperature value was found by establishing the relationship between the brightness value of a specific wavelength and the wavelength itself. Okay? The wavelength value itself, which is the color. So again, the temperature value was found by establishing the relationship between the brightness value of a specific wavelength changing on a curve. The curve is called Planck blackbody curve, which is visualized here on this lower left illustration. Looking at the illustration to the left, and this is a sketch that is correlating between, or it's presenting the relationship between the brightness of a wave with its wavelengths and their relationship to the temperature. So we notice that for longer wavelengths, lower frequencies such as the red wavelengths is a longer wavelength with a lower frequency. It would require a much brighter intensity for it to reach 5500 Kelvin. So for a lower brightness or weaker brightness, it becomes much colder. Meanwhile, for lower wave or shorter wavelengths, higher frequencies such as the blue one here, you notice that it reaches 4500 kelvins even for a brightness as low as 300 kilojoule per nanometer. As you go shorter in wavelengths or higher in frequency, such as for this cyanic blue one, it can reach 4000 Kelvin even for a brightness as low as 190 kilojoule per nanometer. If we look at the formula, so the temperature is given by 289,700 divided by lambda in nanometer. This is the correlation between temperature and the wavelength. Tk, temperature in Kelvin, is equal to temperature in Celsius plus 273, because here we're measuring in Kelvin. So lambda max in meters, the wavelength in meters, is given by 2,890 times 10 to the power of minus 3 divided by the temperature in Kelvin. So in other words, when you have the wavelengths, you can get the temperature of the star from it, which is very important. So we get the brightness, and we already know the wavelengths from the color. From that, we can extract the temperature that is being at play. Observing the chart, again, we notice that higher frequencies, shorter wavelengths, present higher temperatures at lower brightness. In other words, smaller stars that are in the blue range are hotter than their peers having a red color. On the other hand, stars with longer waves meaning lower frequency in the red range, they will need to be brighter, of larger size, larger diameter of disk that is being perceived or detected from the Earth, like red supergiants, to be as hot as the blue ones. To give a comparison in nature, when you burn wood, the fire color would be yellow to reddish, and it's a cooler flame with an incomplete combustion that you can pass your hands through without burning it immediately. It can tolerate passing your hand through that type of fire without getting burned. Just like when you pass your finger across a candle flame. The same concept. Why? Because it is much colder. And from the color you can derive that it is a lower frequency, longer wavelength. Because we're talking about the range of reddish color, reddish flame. But burning methane will display a blue torch with a complete combustion characteristic, burning much hotter, much faster, without residues, which makes passing your hand through that type of fire for the same amount of time that you do it for fiery wood much dangerous, and actually you can get burned, because the fire is less tolerable and much hotter, leading to serious injuries in such case. This is due to the fact because if you notice something, the blue torch actually from a wavelength perspective is close to blue and ultraviolet light, which is the range of light that has high frequency, shorter wavelength. So it carries much more energy and it is much hotter than the red flame, which falls in the specification or in the range of longer wavelengths, lower frequencies having lesser energy. So they burn much cooler than these hotter frequencies such as the blue one. Using the star luminosity, Einar Hertzsprung from Danish origins and Henry Norris Russell, American, independently studied stellar properties in the early 1900s. Hertzsprung plotted temperature versus absolute magnitude for stars in clusters. Russell did the same but plotted spectral type versus luminosity for nearby stars with known distances. Both of their works led to combined HR diagram showing the relationship between the luminosity of a star, its temperature, and its cluster type. For example, you have the blue giants, the white dwarfs, the red giants, and the main sequence. Let's analyze this diagram. First, you have the main sequence. These are those who follow a diagonal pattern in which the ones having the lower temperature will display a dimmer luminosity, the ones to the right. Meanwhile, for the ones having much higher luminosity, they would be to the left. So most of the stars lifetime spent in the main sequence. So these are the grown-up, developed stars that will spend most of their lifetime as an ordinary main sequence star. Of such is our sun. And you notice here, for the ones having a higher temperatures, they would get, or they would emit a higher luminosity. For the ones that become dimmer, okay, they would fall or drop to lower temperatures while, displaying or emitting a lower brightness, a less intense luminosity. In case it's not visible enough, here you have the hottest temperatures going to 40,000, and then the range drops all the way to 2,500. So to the right you have the coldest stars. To the left you have the brightest ones. So to the left you see most of the stars are of blue color, emitting a higher temperature. White dwarfs. When a star dies, if it had a small to medium mass, it turns into a white dwarf, having a dense and still hot core. So the core is still hot, still reacting, but the brightness had dimmed. Why? Because most of the raw elements that cause a nuclear fusion so bright, such as the hydrogen, these have completely transformed, okay? They are no longer fusing and emitting such brightness. Now the heavier material of the core are still fusing until the white dwarf reaches a final black dwarf state where it becomes cold and no longer any reaction is taking place. So a white dwarf has a dense and still hot core while its outer layer has been expelled or shedded. Its fusion fuel has been exhausted. It's no longer fusing the way it used to. For the fusion of the heavier elements or materials, it's no longer producing the gamma rays, which is the photonic emission, the way that lower weight materials or elements such as hydrogen does in early stages of the star development. This is the main reason why you would no longer see, okay, this brightness for when it comes to white dwarfs. So they are still very hot, but they are not as bright as you would suppose. They don't follow anymore the law or like the pattern of the main sequence where you would have for hotter temperatures, brighter stars. Why? Because the elements that are still within the core, that are still fusing, are the heavier elements that are no longer producing light. Now, some of the reactions might still be conducted by elements that are not the heaviest elements, and these would produce some light photons, okay? Some of the few reactions that are still remaining, some of the elements that have not fully transformed into heavier elements might still be producing some small amount of light. But eventually, this will recede and would be completely depleted, leading to only the heavy elements reacting, producing only heat, and eventually these would be like completely transformed into the final state of iron, where no longer you can have any sort of final, so to speak, reaction, any further reactions, okay? So that would die eventually quickly, forming or transforming the white dwarf that is very hot into a black dwarf that is cold right now, and that would be the final state. Altogether, while as a reminder that the external shell, the external layer would have been shed away as the core had receded. As for red giants, these represent the latter state of a star at the verge of the end of its life cycle. So the core contracts as the fusion process that pushes it outwardly runs out of hydrogen. So there's no longer enough fuel for the fusion process to counterbalance the gravitational pull. This leads to a detachment of the outer layer as the core contracts. So you have the outer layer becomes more distant from the inner core. So the gravitational pull is no longer able to hold it back. Okay, it's strong, but it became now focused at the center. So the external layers have become detached from this central core. This leads to a detachment of the outer layers from the core. They are shed away, so they expand and start to cool off. This will form into the red giant. So you have an inner core detached from the outer core that is reddish right now, that starts gradually cooling down. So the hydrogen continues to fuse in a shell around the helium core. Helium starts heating up and fusing into a heavier core. That would be the helium fusion, okay, and it would lead to carbon, oxygen gradually into heavier elements. As for red supergiants, they are the latter state for massive stars, generally similar to red giants, except their core contracts and heat up at higher pressure and higher temperature, leading to an iron core. The final core type would either be a neutron star or a black hole after a massive supernova explosion. That would be the difference. So unlike smaller stars that would end up as a white dwarf then as a black dwarf, supermassive stars, they are transformed into super red giants, unlike the red giants, the normal red giants. Then they would contract into an iron core that will implode and explode, so it would bounce inward and outward, exploding into a supernova, leaving a neutron star or a black hole as a final remnant. Of course, while the external shell would have been shed away from the core, okay? That would form also a new nebula. These massive stars, usually at least 8 times greater than the Sun, witness a fusion from carbon, neon, oxygen, silicon, and iron. How can we figure out to which cluster a star belongs? We first check where a star belongs on the HR diagram, and we see if it does fit on the diagonal sequence path. If its age and metallicity, so how much metal there is, if its age and metallicity measured from the spectrum match the cluster's properties, then it most likely belongs to that cluster. We measure the star's motion, radial velocity, and parallax to check its conformity with the cluster. So, is it supposed to be there or not? Okay, so we need to match up the metallicity, like the chemical makeup, along with the star's motion, radial velocity, and parallax observed from the Earth. So in a nutshell, we see where it sits on the HR diagram, we match it with the known clusters, and verify it based on its motion and chemical makeup. Measuring distance through luminosity. So the flux F, which is how much watts or how many watts per meter square are being received from a captor that is detecting a star from a distance, of course. Flux F is given by the luminosity of the star divided by 4 pi d square, where d is the distance to the star. D is given by the square root of luminosity of the star divided by 4 pi times F, with F being the flux, measured in watts per meter square. Measuring the radius and area of a star. We use the Stefan Boltzmann law that relates the luminosity of an object to its temperature in Kelvin and its radiating area. So Stefan Boltzmann formula is L, luminosity, is equal to area of the star, times sigma, which is the Stefan Boltzmann constant, given by 5.67, multiplied by 10 to the power of minus 8 watt per meter square per Kelvin to the power of 4. So L is equal to A times sigma times T to the power of 4. T is the temperature in Kelvin. So L is equal to 4 pi r square, which is the surface of the sphere. It's not the surface of the disk from our vantage point, it's the surface of the sphere of the star, multiplied by sigma, which is the Stefan Boltzmann constant, times T to the power of 4. So A is equal to L divided by sigma T4, R is equal to the square root of luminosity divided by 4 pi sigma times T to the power of 4. Measuring the radius of stars similar to the Sun, or should I say in relation to that of the Sun. This is inspired by the formula of Stefan Boltzmann. So we can get the radius of a star based on that of the Sun from the Stefan Boltzmann formula. R divided by R of the Sun, this is O dot by the way, a symbol referring to the Sun, is given by square root of luminosity divided by 4 pi sigma T4 for the star to be measured, divided by square root of luminosity of the Sun over 4 pi sigma T4 of the Sun, temperature of the Sun in Kelvin to the power of 4. Let's reduce this fraction so we can remove 1 over T4 outside of the square root. So R divided by R of the Sun is equal to 1 over T squared times square root of L divided by 4 pi sigma over 1 divided by T squared of the Sun times square root of L Sun divided by 4 pi sigma. If we raise all of that to the power of 2, or actually if we remove the square root here and we place it as to the power of 1/2, so you get finally R divided by R of the Sun is equal to L divided by the luminosity of the Sun to the power of 1/2 times temperature of the Sun divided by the temperature of the star squared. From this relationship and as a comparison, we can get the temperature or the radius of another star in relation to that of the Sun. Hubble law and redshifting. Okay, so Hubble law is given by the velocity in a certain direction of the expansion or a galaxy moving away is given by h0, which is the Hubble constant. V is the recession velocity from the redshift as a galaxy is moving away from the observer, times d, which is the distance in megaparsecs. V also has another formula, which is c times z. C is the universal speed of light, approximately 3 times 10 to the power of 8 meter per second, times z, which is the red shift. Imagine you're standing at a side road and a car is moving in your direction, okay, with a loud music playing. If you listen with keen ears, you would start noticing that the rhythm of the music accelerates as if the frequency is increasing and the wavelengths are becoming more compressed, smaller and shorter, okay, as a wave compression process in the time-space domain as the car gets closer to you. You are the vantage point in such case. But once it passes by and starts getting further, the music rhythm starts stalling and dilating as a broken tape, okay? In such case, the frequency decreases, the wavelengths becomes greater, larger, longer, okay, shifting upwards. So this is what is called Doppler's effect or Doppler shift. Okay, we're gonna derive from that the Doppler shift. This is what we are counting on in order to measure the recession of a galaxy as it moves away from us. What applies to sound frequencies is the same thing for a luminous object. As it travels away from a vantage point, its wavelength begins to stretch and increase opposite to its decreasing frequency. A changing frequency of light means a change of color. In the case of an expanding universe, the color of the galaxies moving away from us will shift from blue, green to red, even to a radio wave that's no longer detected or detectable by our eyes. It falls outside of the visible range. So as they move further away, the wavelengths starts stretching, changing the frequency as well. This is due to the wavelength dilation that we call Doppler's shift, okay, or Doppler's effect. The receiving velocity, which is the altered speed of light, is obtained from the following Doppler shift formula. This works for smaller redshifts, as a note. So V is equal to C times Z, Z being the redshift. V is equal to C multiplied by delta lambda divided by lambda, which is the change in wavelength due to the displacement, not displacement, due to the motion of the galaxy divided by lambda, which is the original wavelength value. So lambda is the original value of the wavelength. Delta lambda is the wavelength shift difference due to a galaxy or a shining object moving away. And c is the original speed of light. This is how we can get the receding velocity. If we place that in the first formula, which is v is equal to h0d, we can get the distance, which is equal to velocity, receding velocity, divided by h0, which is also equal, writing it in another format, c times z divided by h0, with z is the redshift, okay? Z is actually the redshifting. For larger redshifts, we need to use the relativistic Doppler formula based on Einstein's theory of relativity for receding light, which is the light moving away. F observed, frequency observed, is equal to frequency emitted times the square root of 1 plus v over c divided by 1 minus v over c. Lambda observed, it can be written in a different way, which is lambda observed is equal to lambda rest multiplied by the square root of 1 plus v over c divided by 1 minus v over c. Now we need to make some changes to this formula to extract from it the redshift. So what is the redshift anyway? What is z? The redshift is actually lambda observed minus lambda at rest divided by lambda at rest, or delta lambda over lambda at rest, which is the original wavelength of the signal. So, at first, we need to place lambda observed minus lambda rest, which is equal to lambda observed is already lambda rest times square root of 1 plus v over c divided by 1 minus v over c, correct? So that's lambda observed minus lambda at rest. This all together is lambda observed. Remember, we took it from the formula here. Next is we divide the entire equation by lambda rest. So you get lambda observed minus lambda rest divided by lambda rest is equal to lambda rest times this here, square root of 1 plus v over c divided by 1 minus v over c minus lambda rest divided by lambda rest. This quantity over here, lambda observed minus lambda rest divided by lambda rest, is simply delta lambda over lambda at rest, which is, in simpler terms, the redshift z, equal to, here we can factor out lambda rest. So you place lambda rest here on the outside of the equation times the square root of 1 plus v over c divided by 1 minus v over c. I'm sorry, the entire equation here is under the square root, minus 1 divided by lambda rest. You factor out lambda rest, so what remains is square root of 1 plus v over c divided by 1 minus v over c under the square root minus 1. And this would be the redshift. We can also make some changes here by moving minus 1 to the left. So you get z plus 1, then you raise it to the power of 2, we get rid of the square root. After that, okay, we can expand it, the entire formula, so you get eventually z plus 1 squared minus v over c times z plus 1 squared is equal to 1 plus v over c. So we simply took this factor here, this ratio, and we multiplied the denominator by, or to the left of the equation. This leads us to z plus 1 squared minus 1 is equal to v divided by c. You can work on it on your own, okay? You can expand it, it's so easy. Plus v over c multiplied by z plus 1 squared. Eventually, okay, z plus 1 squared minus 1 equal v over c times z plus 1 squared plus 1. We get v over c is equal to z plus 1 squared minus 1 over z plus 1 squared plus 1. And finally, the recession velocity is equal to c times z plus 1 squared minus 1 divided by z plus 1 squared plus 1. You place it back in the formula where d is equal to v divided by h0, so the distance is equal to c divided by h0 times z plus 1 square minus 1 over z plus 1 square plus 1. And of course, again, the distance is in parsecs.